Hey physics students, welcome to another edition of Rapid Review for Honors Physics. Today the topic is problem solving with friction, both static friction and kinetic. Let's take a look at what we already know about static and kinetic friction. The equations look similar, the only difference being static friction uses the less than or equal, kinetic friction is a constant. Okay, so in review, static friction, it's always exactly what you need to oppose the applied force up to some maximum. And in review, kinetic friction is simply a constant. It's something that provides an opposing force to the direction of motion, and it may or may not be balanced with your applied force. We saw some examples as shown here in the right-hand column. We've reviewed those in the prior episode. We also ended the prior episode with a problem-solving approach. We said in order to solve any problem involving motion, we first have to figure out whether we're in static friction land or kinetic friction land. So let's use this video today to solve some problems. I'm going to start with a classic example, right? It's a block on a table and there's unapplied force. Here we have a wood block on a wood table. I already looked up the coefficients of static friction and kinetic friction for my possible use looking forward, okay? And apparently I've been given this information where an applied force of 22.2 is put in and I'm given the mass of the block. This is all given. Let's get to work. I draw a force diagram for that. I start my calculations. I'm trying to figure out what the force of friction max is. If you work backwards, you'll see in order to do that, I need the normal force. But in order to get the normal force, I need the F sub g, which is the weight, right? So I start out by looking for F sub g, which is simply mass times 9.8. Then I look at the force diagram, and it's evident that F sub n is F sub g in this case. It's not always true because there might be other vertical forces. In this case, it's quite simple. They are equal. And then finally, I can calculate Fs max by multiplying the static friction coefficient with F sub n, and I get 19.6 newtons, which is, that's less than my applied force of 22.2. So I win. My applied force is bigger than the maximum possible force of static friction. So this thing is sliding. That's step one, right? We haven't solved the whole problem. Let's see what else is happening here. We know it's sliding, and we're going to take that information. Everything we saw already is here. I just grayed that out. And then I try to figure out, now that I know it's sliding, what is F sub k, the force of kinetic friction? That's an easy calculation. In this case, it comes out to 9.8 newtons, and I am in a final situation that looks like this. I'm showing now all the numbers, okay? The forces are unbalanced, so the block is definitely accelerating, and even though I didn't ask you to calculate the acceleration, you could easily do it. You could just look at F net in the left and right direction and divide by the mass, and you would know the acceleration. So that is what happened with me pulling on the block and getting a sliding situation. Now it might be different. It might be that the block was static, in which case there's a different path we have to go. Let's take a look at that path in the next problem. I've got a cardboard box on a wood table. I had to look up online the coefficient of static friction and kinetic friction for cardboard and wood, and I found this online. It's interesting. Why would you want to know this? Well, truckers need to know this, right? They put a cardboard box with a washing machine down on the wood-floored panel truck, and they have to start driving away. They want to know, is this thing going to slide around or not under normal braking conditions? So there's an example application of this knowledge. Let's come back here to the calculations. The initial part of this analysis is very similar to what we did before. We're just figuring out what Fs max is, and we found it, and we compare that to my applied force of 22.2. In this case, friction wins, so it's static friction. And the force of static friction is not 24.5. It's so tempting to say it's 24.5, but remember, that is the maximum possible force of static friction. It's not what you're getting in this situation. If you look at the picture again, what you're getting is whatever you need to counteract my applied force of 22.2. So in this case, the force of static friction is 22.2 newtons. Be careful of that. Easy to get mixed up. There's our final situation, and the block is not moving, and the forces are balanced. So we've seen a problem-solving approach here that asks us to first determine whether the object is moving or not, and then go down the appropriate path of either static or kinetic friction. I have two final comments I'd like to make. One is you can determine these things experimentally. So if I pull like I was before, if I pull and not moving it, I can calculate the coefficient of static friction. I won't go over these equations, but you've probably done something similar in a lab. And if I pull at constant speed, I can determine experimentally the coefficient of kinetic friction. Again, these are measured results, and I won't go over the calculations, but you can pause the video if you'd like to review that. You might find this handy. I made this for my students. This is a summary of everything we know about forces and acceleration and friction and all of that. If you're like me and you like to see everything all in one place, you might find this useful. If you don't find it useful, you can ignore it. It's a summary of a lot of information we've seen in multiple presentations. I have one last thing I almost didn't dare to show you, but I feel like I need to because there's always a couple students who want to ask about this. If this next information confuses you, totally ignore it. In fact, you don't even have to look at it. It's not going to be on the test. But FYI, we've seen this graph where we move in a direction of applying more and more force, or we could do less and less force, it doesn't matter, but as long as we're on that line, we're in static friction land. What we did in the lab, I've never shown you this, but the action in the lab when you did kinetic friction was you gradually pulled up harder and harder. You were on that green line that I have labeled static up until you reach the point of maximum possible static friction. Then what we never showed you, and read carefully the axis names here, force of friction versus force applied, what happens is the thing starts slipping and suddenly the friction force decreases down to F sub k because it's sliding. At that moment in time, your applied force is greater than F sub k, briefly, because it's right here. And then you quickly, as a human being who was instructed to pull at constant speed, reduce your pulling force until you get down to that big red blob. Okay? I would like to do that explanation in a longer video at some point in more detail. The topic is called hysteresis, and I won't go into further detail here, but I find it really interesting, and I hope to do a special section on that in the future. That is all I have today about problem solving with friction.